guys, welcome. Yeah, so as I said in the last video, these 4 videos are meant to be watched in order, and this is the third. So that means that there are 2 videos that you should have watched prior to watching this video, and in the second of those 2 previous videos, we covered the distinct real roots case. That's in the last video, we covered the distinct real roots case. And so then natural here, we consider the distinct complex roots case. And this video is going to start in much the same way that the last video started. So these 3 items are identical in the last video and in this, and in fact they will be the same in the next video also, because, well, in all 4 videos we're discussing solving differential equations of this form, which are called second order linear homogeneous constant coefficient differential equations, these guys. And in prior videos, in the previous 2 videos, we talked about how, in particular towards the end of the first video, we talked about how differential equations of this form lead to a characteristic quadratic, also known as characteristic polynomial or characteristic equation, which is this. It's easy enough to get from this to the characteristic quadratic. Now, as it is a quadratic, this characteristic equation will have 2 real roots, the subject of the last video, 2 complex roots, the subject of this video, or 1 repeated real root, and that's the subject of the final video, the next video. Okay, alright, so let's get on with it with the 2 distinct complex roots. And so those 2 distinct complex roots will be of this form, right? That's of the form a plus bi, and for reasons you can see, we didn't want to use a and b, so we're using lambda and mu. So lambda plus mu I, and plus or minus, that comes automatic from the quadratic formula. When you're solving a quadratic that has 2 complex roots, it's going to look like this, right? For some constants lambda and mu. And so our solution, since it's going to be of the form y equals e to the rt, our solution, and these are the 2 r's, are going to look like this. R1, where we have lambda plus mu I as being R1, and therefore R2 is lambda minus mu I, right? You can rule reverse lambda plus mu I and lambda minus mu I, which is you can interchange where they appear, and like obviously it doesn't impact what we're discussing here. Okay, cool. All right, but then notice that this here, it says e to the lambda x times e to the mu I x, right? If we used exponent rules backwards to go on this, what I'm saying is y1 can be written as this, because, well, when we have the same bases and different exponents, we add. So if we add the exponents here, we get back to this. So this here is identical to this, which is our y1, right? Because what we're going to do is recall in this part what is called Euler's formula, right? And what Euler's formula says, and I have a video proving Euler's formula, but what it says is it's that e to the I theta is equal to cosine theta plus I times sine theta. The proof is really neat and straightforward if you know calculus 2, and so you can check out that video, but this is true. Okay, cool. And notice that this is e to the power mu I x is in the form e to the I theta. If we lead with the I, it's just mu x is the argument theta, right? Okay. And again, put the I in front, and you can see that this here is in this form where theta is mu x, right? And so we're going to exploit that, right, to the end of showing that, again, using what I just said, that y1 can be written like this. I'm going too fast now. y1, this guy, and then this guy here, which is this guy here, which can be written like this, where the I is leading, has theta being mu x, and so just using Euler's formula, right? Okay, cool. And then next we see that e to the minus I theta, which is just a modification of Euler's formula, will have us put a minus theta, so it's I times minus theta really. So the theta here and the theta here will be replaced with minus thetas, both, right? Because what we're doing in this is replacing the theta with a minus theta. The minus sign is not really in front of the I, it's really with the theta. Okay, but then we know cosine is even, so cosine of minus theta is cosine theta, and sine is odd, so sine of minus theta is negative sine of theta. And so using that, we can write this more succinctly, that is e to the minus theta. We can write it more succinctly as okay, that was the lights flickering. I don't know how else to explain that, but yeah, like basically this here, from what I said about cosine being even and sine being odd, turns into this. And so what that means is that our second solution, y2, which is this here, can first be easily seen as e to the lambda x times e to the minus mu ix, and it is for wanting theta to be minus mu x that we looked at this modification of Euler's formula, right? Okay, and so using this right hand side in place of this, which is in place of that, we see that we could write this for y2. Okay, and then now there's some really nice symmetry. Look at what y1 and y2 are like. Like this part, e to the lambda x is the same, and this here is the same as this, and this here is the same as this. The only difference is that plus right there and that minus there. And since in our solution to the differential equation and y, we would like to not have complex numbers, so we don't want the imaginary unit I to appear in our answer, what we could do is we could add y1 and y2. Because remember, if we have two solutions, y1 and y2, then their sum will also be a solution. So just to avoid having an I, if we add y1 and y2, y1 plus y2 will be, well, the sum on the right hand side. And notice that we're just going to get twice e to the lambda x times cosine mu x, because, well, this here and this here are identical, but one with a plus, one with a minus. So when we add, they go away. Okay, so cool, because now if we take, since we have 2 right there, if we take half of y1 plus y2, this is what we're going to get. We're going to get that half of y1 plus y2, and we need space, so is going to be equal to this. Since this is made of the sum of two fundamental pair of solutions, and multiplying them by a constant, this here also is a solution. It doesn't have an I in it. So we're going to take this to be one of our fundamental pair, and we're going to create another fundamental pair. And remember, y1 and y2 being fundamental pair, in this case, comes automatic from this characteristic quadratic having two distinct, and in this case, two distinct complex roots. So the distinctness of the roots of the characteristic quadratic is what's allowing us to claim that y1 and y2 are a fundamental pair. Yeah? Okay, cool. And on the other hand, if instead of adding y1 and y2, we subtract them, then what we're going to get is, well, you can do the subtraction more carefully, but basically distribute this e to the lambda x in this part and this e to the lambda x in this part and subtract them carefully, and what you're going to get if you do that is you're going to get this, which is y1 minus y2 is equal to this. Now, if we divide both sides of this equation by 2i, that is, if we multiply both sides of this equation by 1 over 2i, then what we're going to find is that 1 over 2i times y1 minus y2 is going to be this, and this here does not have an I in it, so we like that, and so this is going to be how we're going to make our second, or this is going to be our second solution coupled with this first solution. So this is kind of like our y1, and this is our y2 in the previous video, but clearly we made this of y1 and y2, so it's like some other new name. We're going to call it u, and we're going to call this v. Yeah? But both u and v are made of a fundamental pair of solution, and in turn it turns out that they make u and v make a fundamental pair themselves. And that means, again, that the Wronskian is not 0, and you'll have to wait for a future video to understand precisely what that means. But now that you've got u and v, and you get to u and v exactly as we have done so far, and I'm going to give you an example to make it more concrete, but yeah, once you have u and v, then your general solution is going to be a constant times u plus a constant times v. Yeah, and as I said, I will provide you a concrete example, and so let's get to that. Now, suppose this is the differential equation. This is the initial condition. We've been through the characteristic equation in the past, so we don't need to discuss it. It's easy to see that the characteristic equation is this. And if you use the quadratic formula or whatever other methods you know for solving quadratics, what you're going to find is that the two r's that solve this quadratic are going to be 4 plus I and 4 minus I. And comparing that to lambda plus or minus mu I, it's easy to see that lambda is equal to 4, and mu, which is the coefficient in front of the I, has got to be 1. Right? So it's easy to see from here, from our solution, that lambda is equal to 4 and mu is equal to 1. Okay, cool. And so as soon as you have lambda and mu, look at how easy it is to solve these now that you have the whole tool box at your disposal, everything that I said prior. It's literally this simple, which is you take your lambda and your mu, and you replace this lambda and that lambda with lambda, this mu and that mu with your mu, right? And all you need is, well, initial conditions to solve for alpha and beta, so you can say you have the particular solution. But otherwise, as soon as you know lambda and mu, and that you get from solving the quadratic characteristic equation, you're on to basically finishing, which is that now u and v clearly, based on the mu and the lambda that we've got, they will be these guys. And so then you're ready to write the general solution, because the general solution, as I've already said, is just alpha times u and then plus beta times v. And so that's this. And since here we have a couple of initial conditions, we can solve for the particular solution. And for the particular solution, since this is y, we can impose this condition immediately, which is make y negative 4 and make all the x's 0. There's an x there, x there, x there, and x there, right? And each of the 4 times 0 is each of the 0, which is 1. Sine of 0 is 0. Cosine of 0 is 1. And so, again, imposing this first initial condition, we would write this, and from everything I just said very fast, sine of 0 is 0, cosine of 0 is 1, and each of the 0 is 1. This equation immediately tells us what alpha is, which is negative 4. And to impose this second initial condition, we have our y, but we need y prime, so we take the derivative of this. Now, be careful that as you take the derivative of this, you have to apply the product rule in this part and the product rule in this part. So if you do all that carefully, and so this is really an exercise in taking derivatives, what you'll find is y prime is this whole big mess. And y prime is equal to negative 1, so you'll have negative 1 to the left of the equal sign by making x on the right hand side everywhere it appears 0. So when x is 0, y prime is negative 1, so that means that you write this next, and just as before, each of the 0 is 1 everywhere it appears. Cosine of 0 is 1 and sine of 0 is still 0. So taking that into account, this equation is going to simplify very nicely to this, which immediately simplifies to this. Those two zeros mean nothing. And now we know that alpha is negative 4, so we're going to put negative 4 in place of alpha right there. In place of alpha right there. I'm talking what do you call them? Infomercial people. Anyway, yeah. So if you do that, you get that, right? And then that automatically means that beta is 15. And now that you've got alpha and beta handy, you can write the particular solution to this differential equation with these initial conditions, and that'd be this guy, right? Okay, cool. And so it's this easy to solve second order homogeneous constant coefficient linear differential equations when the characteristic quadratic has two distinct complex roots. And the next and final video in this 4-video part is going to be on the case of the one repeated real root. Yeah, okay, cool. I hope you enjoyed this and keep watching. Take care.